Good day, folks. I'd like to talk to you about something pretty important today, basically the root of all our research. So those who have been following me for a while are pretty well aware that I like exploring a little bit all over the place, various switching mechanisms, Bedini devices, magnetics, chemical. I try and go a little bit all over the place. If there's something interesting to explore, because, in Tom Bearden terms, there's a lot more than one mechanism to go after. Some people go after the vacuum energy, some people go after the more efficient switching, some people are into reactive systems, and it goes on and on. So yes, these systems at varying degrees, and you can tell from my research and others that there is something there and something indeed to go after. But something that's very common is these systems are very complicated, and it's very difficult to work with the conditions needed. So always trying to find more simple terms and ways to get what people are really looking for. So at the end of the day, I like showing prototypes and quantum energy and whatnot, but the big idea here is if it's not commercial quality power, nobody really cares, even though you're displaying completely legitimate theory and prototypes, and it works and based on grounded, rooted principles. Someone in traditional mindset will see that, and even if you arguably explain how you can do something with a pure potential, they won't look at you because they just want the watts right away, right? And they're thinking in a closed, normal system where, watts in, watts out. Simple. And it's a linear system. Now, one thing is, before here, I want to explain this, and I've talked about the stuff of essentially, I've explained some of this before, but it doesn't always resonate properly, so to speak, and sometimes it's just the terminology or the way I explain it. But I really want to put emphasis on this because there's always people looking for simple relative solutions, which just because I don't have the garage and the workshop to make it, doesn't mean that it's not relatively easy and it shouldn't be done. So what I'm getting at is I shouldn't ignore the stuff that I really know if somebody else, maybe before me, can get to it. But this is definitely something, if I have an opportunity first, I will do it because it is relatively simple compared. Those who follow the Bedini stuff and everything else, this is relatively simple. And others, in their own ways, have stepped into this as well. And I will get a little bit into that later here. But one thing to remember, folks, is when we're handling traditional systems, power, a transformer in an AC systems, where the mains comes from, or energy, basically. Like Tom Bearden said, which is really silly, there is no actual rule in thermodynamics that say we have to keep this linear system that we've adapted ourselves to. We made it comfortable to make energy systems a completely linear system. So this way here, it's completely predictable with the transformers VI action, easy to calculate, and essentially in the power plant's perspective, it's watts in, watts out, it's easy to meter, right? But with that said, it's essentially still the equivalent of pushing a snowball uphill instead of downhill. They're doing it very inefficiently, but at the expense, essentially, of making a huge profit. It's an established industry. Most of us already know that. Now, they don't have to run the way they run our circuits. But to do that, to fully understand, you have to follow, kind of like what Giles Morin did. Right to the power plant and see what they're doing and how the power actually comes to you. And he made some discoveries with auto transformers and the likes and high frequencies, which I will get into here. A few others in their own ways had made this discovery, but it's like, I don't know, they don't know how to take off with it or explain it in a way that doesn't sound top secret. Or other people like Don Smith, for example, they leave a lot out, and I will get back to Don Smith later, but I have to give this introduction here because I believe this may be one of the most important videos that I've made up to date in my research, because those who want to have basically efficient energy, this would be most practical, simple way of doing it right away without needing basically a rocket science degree to understand what's going on here. So essentially, we're used to normal transformers being basically a power thing. It's being manufactured even. You look at the back of a transformer and you see watts rating in, watts rating out. It's basically universe industry standard. That's how they made energy. But as I was saying, like Tom Bearden was saying, in electromagnetic engineering, in electricians, what happens is in these courses, they teach it in the mainstream way, which is the highly linear system. That's all you need to know. That's all you get. So they don't get the quantum perspective of it at all, even though there's Nobel Prizes and all well-proven systems, especially when you get into nonlinear systems and break the symmetry. This is all proven, but you know, the quantum person doesn't speak to the electrical engineer, unfortunately. So that's why, you know, society essentially trains its workers to do just what they need to do to keep the status quo going, which is kind of sad, really, because they think they know it because they went to school, but they only learn the most minimal, and that's the silly thing. We don't need to operate. There's no rules that say we have to make it linear. That was just to keep it pretty and simple and convenient for the electrical company folks. That's all that was at the end of the day. Now, you ask me, okay, so how do we simply break the linearity of regular transformers? Well, I propose a nonlinear dual system. I call it transformer system because essentially it's a type of transformer, but doesn't use an actual transformer mechanism in the traditional sense, which I will get into. Now, basically what we need, because it's a dual system and it's nonlinear, which fits right into the Tom Bearden philosophy, we need a high voltage DC source, but low current. This is essentially a trigger. So 1000 volts at 5 milliamps, which is about 5 watts. But what we're going to do, folks, is we're going to do something really interesting. We're going to mix it with RF energy. RF energy is like AC, but because it's much higher frequency, it behaves a little bit different. The dynamics of RF changes. Plus, RF is much denser energy-wise than AC fields would be. So essentially, you need an RF generator, 10 megahertz or higher. Below that is not worth it for this effect, okay? So you need a relatively high frequency RF. So we're getting maybe typical like ham radios. You can get 12 volts and get 100 watts. So essentially, it takes roughly 8.33 amps of RF power, current essentially. And what we do here is we mix the two. So essentially a crude circuit here with the RF generator, which is 8.33 amps, 12 volts, the RF out. Very simple concept. This is as most simple as you can get it, folks. C1, which is a simple DC blocking capacitor, which allows the RF energy to come through the plus here, and your 1 kilovolt DC low current input. And then optionally, the reason I say optionally is I like to keep things simple, but you could, depending on what you want to run, some bandpass filtering, obviously. But folks, I hate keeping it complicated. The more you make it complex, the more issues you have. You see, this is what I was getting at when I was talking about Don Smith. Don Smith, in his own ways, understood all of this. But he made it very somewhat deceptive because he didn't get into the core dynamics like we're talking about here, you see? And what Don Smith actually showed us with his coils and his whatever you saw on the surface was like 99% bandpass filtering mechanisms, because in his own ways, his target was, again, what a lot of people like to do, try and self-loop it through inverters and that. Now, because this is not a... Okay, my phone rang there. I'm sorry if I had to really take that call here. So anyways, like I was saying with Don Smith, what we saw was basically all that extra filtering mechanisms to be able to self-loop it, because when you have two systems or more mixing in, it's not the same kind of energy anymore. So not anything can operate off of that. So you have to stick to relatively analog loads, lamps, rectifiers, charging battery banks, capacitors, that sort of thing. When you start trying to add stuff, in other words, this solution, folks, is not like a generator you run in your backyard and plug your computer into. It's not really that compatible energy. But as far as an analog load is concerned, it's not going to know the difference. So you can take advantage of that. So that's why I say keep it simple. And of course, the more you add, the more of a loss and the more complications. So like Bedini says, never mind trying to self-loop it if essentially we can get 80 for the price of 1. That's significant. Stick with that, right? So makes it a lot more simple. RF generator, your 1 kilovolt, your load, and the bandpass, well, we might not even need it. And that's it. Your load here could be a heater. It's analog, won't have any problems with this kind of energy. It could be light bulbs, it could be lighting, it could be a rectifier charging a whole whack of 12-volt batteries for later. Again, you do the Bedini, 80 for the price of, sorry, 1 for, tongue twister here. You get 80 for the price of 1. And stick with that. Keep it simple, and then it just works. Then you can do whatever you want after with the batteries, run them off inverters, run your traditional circuits, and when the traditional battery needs recharging, then put them back in this. It's just, and even for a power plant application, this would be good, you see? So looking at the dynamics here, how I got to this, we have to look basically simple Ohm's law here. So power is determined by V times I. So in this scenario here, we have 1,000 volts times 8.33 amps. You see, 8,330 watts. Gain 79.36, or nearly 80 times input power. The COP 83.33. Efficiency 7,936%. And of course, if you follow this, and I've got that in the I would recommend, by the way, I have a PDF file to follow along, and there's charts that show you as the voltage increases, your gains increases. So all you have to do really is engineer your requirements and you're good to go. So that's essentially what I wanted to explain, but first I gotta get into more of the details to make sure that this really resonates with people here. And I just want to make sure my camera is rolling, so I'm just gonna, yes, it's rolling. Awesome. Okay, so there's the PDF file where the first few pages basically is what I've explained here. So what is happening physically? So we're leveraging the dual source here in a way that bypasses the limitation of traditional power systems. The high voltage DC source sets the potential difference, 1 kilovolt, and the RF current injection provides the actual current needed at high voltages without reducing due to step-up transformation. So we completely decoupled from this linear transformer VI action, which is totally optional, by the way. Crazy, but that's what it is. So of course that 8.33 amps at 1 kilovolt is a huge amount of power, 8,330 watts. So the big deal essentially here is this bypasses any efficiency losses. It allows us to engineer the load requirements dynamically using dual source interaction, fitting right into the Tom Bearden kind of systems here. And specifically, it takes advantages of field effects and nonlinear couplings. So here is, if you don't have it, the power amplification and output versus input analysis. I ran this in the, so you can clearly see that there's a massive gain here. So the key results, obviously we already covered that. So the implications of this concept here. So essentially, by decoupling the voltage and current using nonlinear interactions between the high voltage DC side and the RF injection, we've uncovered a way to achieve massive power amplification. Traditional transformers lose power due to the inefficiencies and the need to balance voltage and current linearly, like I was saying. So we also enhance current without step-down losses. And this also opens the new doors for nonlinear power systems such as discussed by Tom Bearden. So of course there's a whole whack of potential applications here because we're talking basically commercial quality power here. And this is what I was saying. This is what everybody really wants at the end. So by keeping it simple, you might actually be able to get that. So of course it could be good for high power industrial applications, heating, wireless power transfer, energy storage, and even grid applications. So now the thing is, you might look at this and see, this is so, why does this not click in the mainstream, right? Well, essentially, even myself at first when I was trying to calculate this, I got caught in it, and this is what I like to call the linear transformer trap. So basically why this happens in the mainstream here, in a traditional power system or transformer, power conservation, obviously, which we assume P in equals P out. Ignoring losses for simplicity here in this example, this leads us to think purely in terms of watts in equals watts out. And of course, voltage current trade-offs. If we step up the voltage, the current must decrease proportionally and vice versa. This is because the power equation P equals V times I must hold. Example, if we have 100 watts at 10 volts, the current is 10 amps. If we step it up to 100 volts, the current drops to 1 amp to maintain the same power. This linear thinking is also reinforced by how transformers are marketed naturally. They focus on their power handling capacity in watts and efficiency, emphasizing the VI transformation aspect. So how this non-linear system breaks this assumption completely, folks, completely. A high voltage DC source sets the electrostatic potential. The RF current is what provides the high current, which is directly utilized by the high voltage side, which is quite fascinating. And why aren't they doing this, right? So the key differences here is essentially what we have to do, folks, is the bottom line here is mainstream electrical systems, the mains, is literally operated in reverse. So what we're doing is we're building a power transformer completely backwards, okay? So we're focusing first on current and then wattage as a product of that. You see, completely reverse as we normally would, and we work our way from the high voltage to the low voltage. Everything is done backwards, you see? Even the way we power our system, but this is how we end up getting this massive gain. So more about this, the linear transformer trap, as I was saying. This approach does not rely on traditional step-up or step-down transformer mechanisms. Instead, it uses nonlinear interactions between a high-voltage DC source and an RF current injection. Current comes first. We focus on injecting a high RF current directly into the high-voltage environment. Watts are then generated later. So simple calculation, the power P equals V times I is then determined by the interaction of this current with the high voltage field, resulting in a massive power output. Example, 8,330 watts at 1 kilovolt. So a lot here. This is the total reverse of the usual transformer logic. Reverse, where we think of watts in and watts out first and then only consider the voltage current trade-off after. So basically why this non-linear approach can confuse. Actually instinctively applied the linear transformer logic first when I was trying to figure this out, assuming I was trying to figure out loads and whatnot, so that the 100 watts of RF input would be the limiting factor, but I didn't consider the direct injection at first of the RF current in the high voltage field. When I thought about it, I was like, wait a minute. And of course, the nonlinear interaction where the current enhancement leads to a much greater power output than expected. So then I tried to visualize the difference. So if you see in the PDF, there's actually a chart here with traditional transformer behavior versus this nonlinear dual system behavior. So there's the actual plot here. As you can see, regular transformers, and this is ours, where the current stays the same, but how your power factor keeps amplifying as the voltage goes up. So massive gain factor here. So you can download this, by the way. So key takeaways here: in a traditional transformer, increasing the voltage requires proportional decrease in current, limiting the power output. In our nonlinear dual system, the current remains high, leading to an exponential increase in power as the voltage increases. This highlights the current first approach we've introduced, where power is generated by combining the injected RF current directly with the high voltage potential. Now, of course, we were talking a little bit about what's up with the mainstream not adapting to this. It's relatively simple when you stop and think about it, right? There's the solution right there. Well, here's some food for thought here. The entire infrastructure of the electrical grid, from power generation to distribution, is based on linear power delivery principles. Transformers are designed to step up and step down current linearly, following the base rule P equals V times I. The power grid focuses on delivering the specific amount of watts to consumer, which is how utilities measure and bill for energy consumption. The entire billing system depends on this assumption, that the power delivered watts is directionally proportional to the energy consumed. Now, this brings up the obvious metering issue. If the power companies were to use a system like this, where current is enhanced nonlinearly and the power output at the load far exceeds the input power, it would break the existing metering model. Ta-da! The consumer would effectively be getting more watts locally than the grid is supplying, meaning the utilities would lose a significant portion of their revenue because they charge based on watts delivered, not the potential power generated locally. You see? So let's keep it like this, because we can make a lot of money even though we got to generate more power at the source and pollute the environment. That's okay. We'll just do a fake green agenda so we can make more money in investments, which is like completely two-faced, but you know, it's a game they play, right? So the nonlinear interactions, hidden knowledge or neglected innovation. It's possible that the nonlinear interaction we've uncovered are not widely recognized in mainstream engineering, or they have to be known but intentionally overlooked due to economic interests, obviously. You see, large-scale energy companies have invested heavily in traditional infrastructures, the transformers, the power lines, and all of that. Shifting to a nonlinear current-driven system would require a complete overhaul of the grid. There's also a profit motive. The current model is highly profitable because it allows utilities to control and meter power based on the predictable linear relationship between voltage, current, and power. So, conspiracy or conservatism? It's not necessarily a grand conspiracy, but rather a combination of institutional inertia and economic incentives. Companies tend to stick to what's profitable and reliable, even if it's not the most efficient. The shift to a system like this would reduce central power plant loads indeed, potentially benefiting the environment for sure, but it would disrupt the traditional profit model of selling as many kilowatt hours as possible, and they cannot have that. So, of course, the backwards operation of mains power, it's them that's all backwards, not us. So we're actually correct in observing that the current system operates backwards compared to the efficiency potential it could have. The grid focuses on delivering the watts directly, pushing high voltage through transmission lines, and relying on transformers to step down the voltage for local use. This approach incurs significant losses due to resistive heating, inefficiencies in transformers, and the inability to fully utilize the nonlinear field effects such as we've described here. Our method is essentially the forward way of doing it, not the backwards way. By focusing on current injection and utilizing the high voltage potential locally, Our approach would reduce transmission losses and increase local power efficiency. It would enable a more distributed power model where local nodes, examples, homes, businesses, generate more usable power, less input from the grid, effectively amplifying power locally at every node. So a real green agenda or just greenwashing? If energy companies and policymakers truly prioritized efficiency and environmental benefits, they would explore nonlinear systems like this. The current model of central power generation and long-distance transmission is inherently inefficient, grotesquely inefficient if you were to ask me, leading to significant energy losses. Our approach could lead to a genuine green agenda, reducing the demand on central power plants and allowing for more efficient local power generation. However, the focus is often on maintaining profits and managing existing infrastructures rather than embracing disruptive innovations. So we're going to be stuck in this system for a while, folks. We really will be. So what it means for the potential future of energy, it's a potential shift for sure. Maybe word of mouth, social media, or YouTube experiments, as we keep talking about it. It would enable a new class of power converters and distribution systems that leverages nonlinear interactions, reducing the need for traditional step-up and step-down transformers. It would support a more decentralized power grid where local generation, such as solar wind, can be amplified, made more efficient without relying heavily on central plants like we do now. Everything here is a no-brainer if profit is not on your mind. So what's the barrier, right? Big pockets and profits, unfortunately. So the conclusion, obviously, and it's kind of a sad one, all of this here that we just talked about is a major disruption to the status quo. So we can expect more negativity from the electro boom gang, unfortunately, but the important part is I know that you know and that you know that I know, and together we'll get this going, folks. And thank you as always for watching and looking forward to your interactions.